What are the biggest questions that have troubled the greatest minds for centuries? Mysteries that stretch our understanding of space, time, and existence itself. These are some of the biggest questions that keep astrophysicists up at night. Let's unravel these mysteries, one by one. First, dark matter. Planets, stars, galaxies, everything we can see comprises less than 5% of the universe. The rest? It's dominated by entities we call dark matter and dark energy, which make up about 25% and 70% of the universe, respectively. Dark matter is unlike anything we can see or touch. It doesn't emit, absorb, or reflect light. Its presence is inferred only from the gravitational effects it has on visible matter. Without dark matter, galaxies would simply fling apart. The gravitational pull from the matter we can see isn't nearly strong enough to hold them together. This invisible substance exerts a powerful gravitational force, shaping the very structure of the universe. We can detect its existence through its gravitational influence on light, bending it in a phenomenon known as gravitational lensing. This lensing acts as a cosmic magnifying glass, revealing the presence of this mysterious substance. Dark energy, on the other hand, is even more elusive. We see its effects in the universe's accelerated expansion. Back in 1929, Edwin Hubble discovered that distant galaxies were receding faster than nearer ones, a phenomenon evident from the redshift in their light. But this expansion isn't slowing down as once thought. It's speeding up, driven by dark energy. This mysterious force, which makes up most of the universe, acts contrary to gravity and seems to be an intrinsic property of space itself. The more space expands, the stronger dark energy becomes, continuously generating more space. While we have several hypotheses, from exotic particles to a property of space itself, no theory yet fully explains their nature. This is the frontier of science, a reminder of just how much we have yet to learn. Next, antimatter. In our universe, the most unassuming substances often hold the keys to the biggest mysteries. Antimatter isn't just a plot device for science fiction movies. It represents one of the most baffling puzzles in physics. Why does anything exist at all? For every particle, there is an antiparticle, its mirror opposite in charge but identical in every other way. Electrons have positrons, and protons have antiprotons. When matter and antimatter meet, they annihilate each other, releasing pure energy and leaving nothing behind. If this perfect symmetry had prevailed, the universe should have self-destructed moments after the Big Bang, leaving nothing but light. Yet here we are. This leads to the inevitable question, why is there more matter than antimatter? This imbalance, known as the matter-antimatter asymmetry problem, suggests that during the universe's inception, conditions favored the production of matter slightly more than antimatter. For every billion pairs of particles and antiparticles that annihilated each other, one particle of matter was left over, leading to the universe as we know it. The standard model of particle physics, though incredibly successful, doesn't fully account for this asymmetry. Experiments at CERN are trapping anti-hydrogen to compare its behavior to hydrogen, probing the very foundations of modern physics. Our current models are incomplete. They falter at explaining why the universe prefers matter to antimatter and why there is something rather than nothing. Then, there's the question of what lies beyond our cosmic horizon. The observable universe, spanning 46 billion light-years in all directions, is just the beginning. Beyond this boundary lies the unobservable universe, which might be infinitely larger. One possibility is that the universe extends endlessly, filled with a potentially infinite number of galaxies, repeating the patterns of clusters and voids we see. Alternatively, if the universe curves back on itself like a higher-dimensional sphere, traveling far enough in one direction might eventually bring you back to your starting point, a cosmos that is both finite and borderless. As dark energy accelerates the expansion of space, it causes distant galaxies to recede faster than light can travel, sealing off the far reaches of the cosmos and ensuring they remain forever hidden. What lies beyond is likely an extensive, possibly infinite stretch of galaxies and phenomena that could operate under physical laws completely different from our own. Of course, we can't forget black holes, regions where gravity is so intense that nothing can escape. The center of a black hole, the singularity, is where the known laws of physics simply break down due to infinite density and gravity. As you cross the event horizon, the ultimate point of no return, space and time are thought to swap roles, with all paths leading inevitably to the singularity. Here, the curvature of space-time becomes infinite, and all mass is crushed into an infinitely small point. What's fascinating is that a black hole can be described by just three properties: mass, charge, and angular momentum. However, this simplicity creates a paradox. According to quantum mechanics, information cannot be lost. But information falling into a black hole appears to vanish, creating a fundamental clash between general relativity and quantum theory. Some theories even propose black holes could be gateways to other universes through wormholes, but that remains purely speculative. For now, the center of a black hole remains one of the most extreme environments imaginable, a place where our understanding of reality is shattered. Finally, we have the Big Bang itself, the genesis of everything. The Big Bang wasn't an explosion in space, but rather an expansion of space itself. At that first instant, the universe was infinitesimally small, hot, and dense. From this fiery beginning, it stretched and cooled, laying the foundation for the stars and galaxies we see today. Evidence for the Big Bang is overwhelming, including the cosmic microwave background radiation, a thermal remnant from about 380,000 years after the event, giving us a snapshot of the infant universe. As the universe expanded and cooled, quarks formed protons and neutrons, which then gave rise to atoms. But the Big Bang also introduces profound mysteries. What came before it? Is our universe unique or just one of many in a vast multiverse? These questions challenge our understanding of natural laws, suggesting the universe's origins and ultimate fate might be bound by theories we have yet to discover. The more we learn, the more the universe seems to guard its secrets, leaving us to wonder, are we simply the universe questioning its own existence? Thanks for watching. If you're fascinated by the mysteries of the cosmos, make sure to like and subscribe for more deep dives into the unknown.